Can deep sea desalination help address the problem of enough fresh water? Well, there are in progress. Deep sea desalination can indeed pull fresh water from the depths. Companies are experimenting with deep sea tech to produce cheaper, fresh water. Hello, friends. Jim here. So what is this all about? There's some ocean wave activity. From Cape Town to Tehran to Lima to Phoenix, Arizona, dozens of cities across the globe have experienced water shortages recently. And in the next 5 years, the world's demand for fresh water could significantly outpace supply, according to United Nations forecast. Now, several companies are turning to an unexpected source for a solution, namely the bottom of the ocean. Before we proceed, fresh water is in fact becoming a troubled, shall we say, resource. The insufficient, potable, clean water for people on this planet. Some social scientists and political scientists opine that a major global war over freshwater availability and usage could result in the coming years, coming decades, probably some point during this century. It's a problem. We need water, right? Our body's like 70% water. And a lot of the water supply out there, they're full of pathogens, cholera, dysentery, other waterborne illnesses. So this is an issue. We have a water shortage across Africa. Some places in the U.S., some places in Southern Europe. China even. So it's a problem called subsea desalination. The idea is to remove the salt from water in the deep sea. If it worked at scale, the technology could greatly alleviate the world's water access problems. And we should probably say clean water access problems. Costs and energy requirements have kept desalination from going mainstream in most of the world. Early desalination involved boiling the seawater, then condensing the steam, which was a thermal approach. And as you can imagine, that requires lots of energy because you have the heat of vaporization, then the heat of condensation, but it requires a lot of energy input. And how is this often used? Well, yeah, you guessed it, burning fossil fuels, which makes the climate situations worse. So, lots of energy didn't catch on. That methodology was later replaced by what they call multi-stage flash distillation, in which temperature and pressure, quote unquote, flash the salt water to steam. Also energy intensive. In the past 25 years, reverse osmosis has become more common. And by the way, you see this a lot in scientific laboratories. You have a reverse, what they call an RO, basically a faucet. You got the typical hot and cold, and you got an RO faucet using reverse osmosis because a lot of lab procedures require purified water. So what is reverse osmosis? Well, it uses high pressure to push seawater through a membrane where the openings are very tiny that only the water molecules themselves can move their way through. And since salt is a larger molecule than the water molecules themselves, they're left behind. Now, reverse osmosis is more efficient than distillation, but again, it takes a lot of energy to pressurize millions of gallons of seawater and moving it through filters. It's a lot easier if you're just having a little, 3/4-inch copper pipe bringing in water, and you move it through an RO that's mounted in the wall of your lab. That's a lot easier to operate. But when you're trying to get millions of gallons to provide fresh water for people, it becomes a different story. So people started thinking, what would happen if we let the movement occur naturally by utilizing the pressure already inherent in oceanic water that's hundreds of meters down? You don't have to create pressure; it's already there. The rough conversion is that for every basically 10 meters or so of depth that you go vertically down in the water column, you increase the atmospheric pressure by 1. So, you're at sea level, that's 1 atmosphere, you go down 10 meters, you're at 2 atmosphere, you go down to 20 meters, you're at 3 atmospheres, so on and so on. So if you're going down 500 meters, you're looking at 51 atmospheres in essence. And that notion of utilizing the pressure found at depth is the underlying notion behind subsea desalination. So now you can take your reverse osmosis pods, now you can take them to depths of about 500 meters and let the pressure naturally do its thing. So the immense hydrostatic pressure, separates the water from the salt. Then you take that purified water and pump it back, back to the surface, back to shore. Well, sounds great in concept, and there are multiple prototypes already testing this. How do you make this large scale and cheap and so forth? Well, one of these companies is Oslo-based Flotion. Its founder and CEO, Alexander Fuglsang, says there's no revolutionary new technology behind this business. It's essentially a subsea pump cleverly coupled to existing membrane and filter technology. What's new is the energy savings. Flotion uses 40 to 50% less energy than conventional plants, and modular systems that can be deployed to many deep sea locations without, any specialized engineering. Seafloor has other benefits. This region harbors fewer bacteria and other microorganisms than at shallower depths, and there is little variation in temperature or pressure. The deep sea is really predictable, Fuglsang says. It's the same 365 days a year. Well, not really, but sounds like he's not an oceanographer, so you are going to get temperature and pressure variations. Now, if the operating parameters to use the RO at depth is such that it has a wide tolerance, then the variations in temperature or pressure could fall within the engineered parameters such that he can say it's predictable. What he should be saying is it's suitable for our purposes. It's consistent for our purposes. So I just wanted to make that point. So, if you're doing, trying to do a RO on land-based plants, we'll talk about industrial plants, not autotrophs. They then have to deal with algal blooms, river runoff, storms, seasonal temperature changes, which can change the pressure and change how efficient the whole process is. And less chemical pretreatment of the water is needed at depth. and the equipment is all underwater, so you don't get the NIMBY concerns. Not in my backyard. So, despite its advantages over land-based plants, subsea desalination has several hurdles to overcome before they can try to make this commercial. It's still expensive. Land-based desalination is several times more costly than pulling water from aquifers or lakes. Even at gigaplants in the Middle East that benefit from abundant solar power and large economies of scale. Even if subsea technology cuts the cost of land-based desalination down by 40%, it will still be pricey to obtain potable water. We need to remember that once the water is desalinated, it still needs to be pumped up from depths of up to, now he's saying 600 meters, said Nadal Hilal, who's the founding director of New York University's Water Research Center in Abu Dhabi. And he has studied water treatment engineering for more than 30 years. Early pilot tests show promise, but the technology is yet to be proven at large scale. Affordable renewable energy will make subsea desalination more viable. Improvements in technology will also help. Hilal's research group, for example, is developing electrically conducive RO membranes that keep themselves clean by repelling salt ions and impurities. See, that's the thing. When you're using the RO membranes, yeah, you get the pure water on one side, but you have an accumulation of the salt ions and other species on the other side. And they accumulate enough, and then they plug the holes. So then you have to clean them and so on. So by having electrically conducive membranes, you can basically clear out, especially the ions. So that allows for greater time frames in between doing maintenance, so the maintenance intervals increase. And Fugelsang says that might be 2 to 3 years with the existing membranes. Although proponents of the technology say it would have little effect on undersea life, others urge further research to gauge its impact on marine ecosystems. Yeah, I'm gonna have a bunch to say about that in a moment. Many organisms do quite well at 500-meter depth, says Adina Payton, a professor affiliated with the Institute of Marine Sciences at the University of California, Santa Cruz. The twilight zone, which extends from 200 to 1,000 meters below the surface, is not only home to organisms such as whales, squid, and jellyfish. It's extremely important for many ocean processes, such as the carbon cycle and nutrient cycling. Yes, absolutely. Companies will need to ensure that their water intake and salty brine byproduct, that's my major concern, do not harm marine life or significantly alter these processes. Given the depths required, subsea desalination won't work in just any seaside location. Many coastal cities are situated on wide continental shelves, meaning deep water is far offshore. Coastlines with steep drop-offs are ideal because shallow shelves would require long pipelines, adding the capital and operational costs. So off the western seaboard of South America would be great. East coast of North America, not so. Fugelsang isn't worried about technical or engineering hurdles. He says the industry's biggest challenge will be aligning customers, governments, and financial partners. Flotion is working on what will be the world's first large-scale subsea desalination plant off the coast of Norway, which, with its fjords, has indeed coastlines with steep drop-offs. And he has a contract to start supplying water to an industrial facility in 2026. So this could be upon us quickly. Netherlands-based Waterrise has also secured its first industrial customer with plans to start building a plant in the Red Sea's Gulf of Acaba later this year, and Bay Area-based Ocean Well is testing its prototype near Los Angeles. Long-term government contracts will most likely be needed for subsea desalination to really take off, and they may prove elusive. The water infrastructure industry is quite conservative, Fuglsang says, noting that because new projects are so expensive, nobody wants to be first to go all in on a new technology. Hyalal says he believes subsea desalination could go mainstream and supply water to entire cities, but, he adds, reaching true city scale will take time, conceivably a decade or more. Okay. I left salty brine highlighted. Think of this desalination process as another brine rejection process, which is in essence what it is. Because recall that when sea ice forms, the brine is rejected, and what's left freezes, and you don't have salt in the ice. It's called sea ice because the source is from the sea. But what happens? You've reduced the volume, the amount of the liquid water, but you now have the same amount of salt that you had before, but in a smaller volume, so the salinity increases. And and you've all seen the brine plumes and so forth. Well, here you're squeezing out the water, leaving the salt behind, and you're taking that fresh water and pumping it to the surface. Meaning what? And when you think about it on scale, you're reducing the volume of the water, but now because you still have the same salt content, the same salt amount, you're increasing the salt concentration. What can happen, and in some other practices of desalination plants, you end up creating hypersaline waters. And hypersaline waters harm marine life. So, if you've got ions gathering on one side of the RO membrane, you might want to scrape off those ions and collect it, not let it go back into the water. Because lots of times, in fact, most marine organisms, unless they live in an estuary or shallow locations, most marine organisms are what we call stenohaline, meaning they can only tolerate a narrow range of salinity values. If you're an estuarine organism, where you get the tidal input, the riverine runoff, and so on, where you can see changes in salinity from as low as, say, 12 parts per thousand up to 28 parts per thousand, your physiology is suited to handle a wide range of salinity values. Such organisms are called euryhaline. But marine organisms, 500-600 meters down, no, they're stenohaline. They cannot tolerate a wide range of salinity values. Go too low, the physiology can't handle it. Go too high, the physiology can't handle it. So if you start creating hypersaline waters, you are going to imperil many marine organisms. So that is a concern that I have. That is something that needs to be part of this whole process, making sure that you do not jack up the salinity of the waters from where you're pumping this stuff from. So that's my cautionary note. What do I think of this overall? Well, water is important to us. I still argue that, and this isn't just me pulling numbers out my backside, based on the work of population biologists, humans at 8.2 billion and counting is just too many people on the planet for available resources that can be sustainable. Carrying capacity is between 100 to 600 million. We're at 8.2 billion. So depending on what you take, the upper end or the lower end, we're either 13 to 80 times above the carrying capacity. So it's, resources availability is going to be a major problem. Not just water, but land, food, etc. So this is interesting. We'll have to see what comes of this. But they need to make sure they have a good handle on the hypersalinity issue that I have raised earlier. And what capacity we're talking about? How many gallons of water per day are we talking about? So, oceans may be expansive, but it's not limitless. So use the water. Okay, so what happens to the water? Do you let it, after it's used, you let it run off? Is it then filled with, fertilizer and stuff like that? You're going to have eutrophication. Are you going to, if they do indeed scrape off this salt, do they intend for this water to be returned to the ocean? And if so, do you then put back that salt you removed earlier? So you can try to keep the salinity basically somewhat the same? Need to see more of the engineering details of this. But you have this, Norway, Middle East, LA. You got this happening in several places. So let's see what happens. But those concerns and all the points I just raised in the last few moments must be addressed. Thank you for your time.